I had a conversation with Dr. Sabine Hossenfelder, who is, I guess you'd call a controversial physicist, because in her book, Lost in Math, I think the title is Lost in Math, How Beauty Leads Physics Astray. She basically realized that most physicists, starting in the 70s, got enamored with the notion that the universe was beautiful, that there was something beautiful about its design, about its direction, about its, existence. And that colored their work, and that colored their experimentation, and that colored their theories, that drove physics in a direction over the past 40 years that have really borne no material fruit. And she thinks that physics is in a complete crisis, where physics is no longer something that is something that we're taught. And she's this is a woman that's very qualified. She's the author. She's a theoretical physicist, philosopher of science, and she has published like 80 research papers in the foundations of physics, from cosmology, I'm reading this off right now, to quantum foundations and particle physics. So she's somebody that's been steeped in the discipline, and she, in a lot of ways, feels like she's pissing on a giant parade, but it had to be said, I've heard Eric Weinstein talk about this stuff too. And she started out as a mathematician and then became a physicist. But she was like, I don't know what you guys are doing here. You've got this Hadron Collider in CERN, Switzerland. And so far, after 10 years, we found nothing. That material, I suppose. I mean, the particle physicists would argue otherwise. So I have this long conversation with her, and we just get right into the conversation. I probably should have set things up in a better way about what she's doing. But again, I wanted to talk to somebody that's basically saying, hey, physics is in a crisis. All of you physicists with big names have been wasting time and draining resources because you've been very good politically at garnering those resources. And it started because in the 70s, people realized, well, really earlier than that physics is a very, very dangerous tool in the wrong hands. I was talking to Eric Weinstein on the way here. Physics is dangerous, and we have two just devastated Japanese cities to point to that fact. So if we have these people working in these labs, and we're talking about this with AI now, human beings are very capable of inventing technologies that could mean the destruction of the human race and everything that we know. That's why. And by the way, conversely, it could mean endless possibilities and something incredible. So that's why physics and quantum physics is actually important, and quantum mechanics and the study therein is important. That's why those resources need to go there. But you've got to be studying the right things. And you can't just allow people to go off into these wormholes that bear no fruit. So that's what Sabine and I start talking about. And for the first 20 minutes, we're a little bit all over the place, but I just wanted to start talking. I probably should have set it up better, but I didn't. But I think it's a good and interesting 1-hour interview, so I hope you enjoy it. And without further ado, Dr. Sabine Hossenfelder. You're speaking right now to a true novice when it comes to quantum physics, string theory. It's just for people like myself, this stuff is it's all basically Greek. And I listen to you speak, and I listen to you have these conversations. And I do think that, I've had it explained that physics and quantum physics is a very powerful and in the wrong hands, dangerous thing, right? I mean, we can see what happened in Hiroshima and Nagasaki, and do we have to go beyond space-time and all these questions? But for most of us, it's just usually when you hear quantum physics, we all go, it's too much. I can't handle it. It's too smart. It's for those eggheads over there. But I kind of wanted to speak to you because you seem to believe and seem to articulate the fact that a lot of what we've been doing in physics has been a waste of time. Is that true?
Well, not in physics overall. I usually confine myself to the foundations of physics. So where we're trying to discover something fundamentally new. There are a lot of more applied fields where I think things have been going fine. Stuff like optics, quantum optics, plasma physics, and so on. I think it's going fine. But when it comes to those deep fundamental questions about the nature of reality or what's really going on with quantum physics, as you just said, we haven't made any progress since the 1970s. So on the theoretical side, like experimentally, there have been lots of loose ends that have been tied up, with the ending with the discovery of the Higgs boson like a decade ago.
Right. Why then all the fuss? Like, why can't we just live in a Newtonian reality? And I know the answer probably is because it exists and we have a brain that can comprehend this and that we have figured out that there are quarks. But do you know what I'm saying? That's really the question. What are the stakes here?
You mean why does it matter to push forward in the foundations?
It's an ignorant question, but indulge me, in that.
Well, no, it's a very good question. I wish more physicists would ask that question, because if they were more focused on the outcome, I think they wouldn't have gone down dead ends like string theory and all kinds of other weird stuff, supersymmetry, grand unified, whatever, theories of everything and all that stuff. Basically, we know we're not done with the foundations of physics. As you said correctly in the beginning, physics is a very powerful tool. We've seen this in the past, like you literally unleash new forces on the world. And to me, it's pretty clear that there's something big missing in the foundations of physics, because we don't really understand how quantum mechanics works, what's this all about with the measurement problem and so on. And we can go into this. And if we figure this out, I think it'll give rise to a lot of new technologies. And it'll change the world. And so at least this is my personal motivation. When it comes to other questions like quantum gravity, or is there a new particle which makes up dark matter and so on, I think people are more driven by this curiosity, like basically the need to understand how the universe works. And I understand that. I think it's kind of a primal need. We're part of this universe. We want to understand what's going on.
Yeah.
And there's also you can speculate that in the far future, if we become a space traveling species, maybe we'll actually need to know what dark matter does. But, it's maybe 10,000s of years or longer off. Yeah.
Well, that's right. So when you said it has a lot of promise for new technologies, what do you think? Give me an example of the new technologies that you think it could, if we get it right. What are these new technologies we're talking about?
Well, I don't know what the new theory looks like, but that I've been very interested in the question, is nature really non-deterministic as quantum mechanics suggests, or is it actually something deterministic? We just haven't really figured out what's going on. And let's just speculate that this was true and we actually figure out what's going on and we are able to predict what the outcome of a measurement is in quantum mechanics. Then this would remove a lot of measurement barriers that come from the quantum uncertainty, basically. And so you can see what you can do with this. You can basically, everything that we currently do, you can do it better. So every time quantum uncertainty comes to bite you, you will be able to overcome this with sufficient data collection, basically.
Yeah, you said one of the problems is instrumentation, right? So even the Hadron Collider is made of glass and metal and things like that. So you're dealing with the limitation not only of our own perception, but also that apparatus that allows us to hear and think and see, but also the tools, the very tools we use to measure can sometimes be in the way, right? So
yeah, certainly. So I'm not sure exactly what you're getting at. You're getting at the issue that a measurement always changes the thing that you're trying to actually. Right. So this is kind of always an issue. Like if you're trying to measure the temperature of your turkey or something, and you put in the thermometer. That'll change the temperature of the turkey. But it's such a small change that you don't really care about it.
I was going to say that there are a lot of things we don't get exactly right, but it works. So let me give you an example. Football. In football, the American football, when you measure where it's a game of inches, really a game of yards and feet. But I'm sorry about the metric system. But when you put the ball down, when the referee puts the ball down and says this is a first down or a fourth down, it's you don't exactly know exactly where the ball landed. I mean, we could get NASA out there with their instruments to say actually it's 4 inches back, so that's not a first down, it's a fourth down, and it changes the game. Okay. But that truth isn't that relevant to the game of football. We still watch the whole game. We get so much out of it. And it works. When an approximation works. An approximation bears material fruit. And I would imagine physics is the same way, yeah? So don't get so hung up on all that.
That's right. Physics is all about approximation, basically. And we also, Newtonian mechanics, you've already mentioned this, is an approximation. We know it's an approximation to Einstein's general relativity. And a lot of old theories that we had, they're approximations to better theories, which we have now, which naturally brings up this question, like, are the theories that we currently use also an approximation of something else that we yet have to find?
Yeah, it never ends. So are you, do you think the universe is deterministic or non-deterministic? What's your instinct?
I think it's deterministic, but from an experimental point of view, I think that's not the right question to ask.
Really? Why?
Well, because you can never prove or disprove that it's deterministic or not deterministic. Like, it could always be, if something is non-deterministic, like right now with quantum mechanics, there are just things that we can't predict. How do you know it's really non-deterministic? And it's not just the case that we haven't figured out how to predict.
Yeah.
Right. And if we have something that is deterministic and we can calculate anything, you can always ask, well, maybe there's something that we can't calculate. We just haven't yet seen it.
This is the old question of free will, right? I mean, is it did you actually make the choice, or is the choice made for you and you think you're making the choice, right? I mean, it's similar to that. I don't know. Maybe not, but.
Well, so certainly a lot of philosophers have linked the question of determinism with the question of free will. As you probably know, like there are two camps of philosophers. Actually, there are probably 50 different camps. Yeah. But, the two biggest camps there are the ones who think that free will is compatible with determinism. Those are the compatibilists. And then there are the ones who think that's not the case, and they're called libertarian or something like that. Something with liberty in it, in any case.
Yeah, because the question that this is what I wanted to ask you too, because if you're a strict materialist, then the idea that everything is ultimately measurable seems to come into play. But it does seem that the philosophy camp is broken into two schools. One would be that essentially all knowledge is experience, and then there's another which would say there's something called a priori knowledge, right? There's something that is maybe impossible to measure, something like imagination, something like potential, something like the idea that I get this idea in my head that bears no relevance to the material world, but somehow further down the line, maybe 150 years later, this theorem I came up with actually does bear fruit. Maybe I use it to put a rover on Mars or whatever it might be. So I've always been fascinated with that idea that human beings, seem to have these questions in their minds. Just even having the question in your mind feels deterministic in a way. Maybe I don't know.
Yeah, well...
Maybe it's not relevant.
Well, it's an interesting question because people are now thinking about using AI to prove theorems. And so it brings up this interesting question, like, is it actually a deterministic process? Like, can you actually, so if you're trying to prove a theorem, which might become useful in 150 years or something like this, how do you come up with the proof? And, mathematicians have some kind of inspiration, they have a sudden insight or something like, but where does it come from?
Yeah.
Is it just, are they using something that they've previously encountered and they're drawing some parallel? Are there different techniques to lead a proof? Have they picked up one of those? Or is it actually just noise in the brain that plays into this? Is it actually necessary? So it's a very interesting question. I think we don't really know how the brain does these things.
But you've said that physics, I think, and is in a crisis. Yeah, is that fair? Can you explain why?
Well, so as I said in the beginning, I'm really talking about the foundations of physics, but I think it spreads from the foundations of physics to other areas because, okay, this is a little arrogant of me as a physicist, but I think that physics, and in particular the foundations of physics, are ultimately the source of new knowledge. So if we don't find anything new in the foundations of physics, then at some point progress will run dry in all other areas. Like if you think, for example, medicine, like we're seeing loads of progress in medicine, with new vaccines, imaging technologies, and so on. But what does it go back to? It all goes back to better imaging machines, better measurements, better computers, which go back to better understanding of materials, ultimately quantum mechanics. So, so in my mind, it all goes back to physics, and we haven't yet squeezed out all the water from the tower, or whatever the saying goes. So we're still reaping the benefits of discoveries we've made more than a century ago.
Wow.
But we're not finding anything new. So at some point, it'll just stagnate.
How did this happen?
Sorry?
How did this happen?
Well, I've been thinking about this for 10 years. So I'm sorry, I can't give you an answer.
Yeah.
What I can tell you is where I think things went wrong. And that was sometime after physicists completed the standard model of particle physics. Like on the theoretical side, it was sometime in the 1970s, and I won Nobel Prizes for it, and so on. And they had some issues with the standard model. It wasn't as nice as they wanted it to be. So they were trying to make it nicer. And this is where this idea of grand unification comes in, that Eric is working on, and also the theory of everything, which is even better than the grand unification, basically.
Supersymmetry and things, yeah.
Yeah, exactly. And so I think at the time it was a reasonable thing to try. And they did this like in the 1980s, and it didn't work. Okay, so they came up with some theories, they tested those. They didn't find anything. It didn't go anywhere. And at this point, I think they should have thought about, is this a good thing to do? Like, are we getting anywhere plausibly? Can this even work? This kind of theory development, just guessing some new particles and then building a detector. But they didn't. Instead, what they did was they revised those theories and then built new detectors and looked for those particles or decays or whatnot. Again, didn't find them. And then they did the same thing over and over and over again. And they're still doing this, even though it obviously doesn't work. And so I think that sometime, in the 80s or 90s, and we can discuss exactly when, this just became totally insane, but they never stopped it. And so there's something, this self-corrective mechanism that you expect science to have isn't working.
Yeah, I've heard that's because the people you're probably talking about string theory and the amount of energy and time and money and grant money that was given to this pursuit of string theory that seems to have come up in the past 40 years with nothing material. And yet you have these sort of eminent physicists with big names that Eric is happy to mention. I don't know these people, Michikaku and Penrose, all these guys. I don't know these people, but they were very good at attacking people that were attacking them, or at least had an alternative theory. And so they're still at it. Yeah. I mean, it sounds like they've got tenure, very cushy positions as these very smart physicists working on, the nature of reality. And people like yourself and Eric and other people are going, wait a minute, guys. Hey, guys, you've been working on this for 40 years. I don't have anything I can hold in my hand, Like this is just a whole bunch of theorems that go nowhere. So it sounds like it was an echo chamber. It sounds like it was an echo chamber, and it sounds like it was almost a mental masturbation. I don't know. I might be being very unfair. But this is at least people who are smart enough to understand this stuff, like yourself, are saying that's exactly what was going on. Yeah.
Well, yeah, kind of. So first of all, I think one of the people you mentioned was Penrose. Penrose has actually been one of the few critics.
Oh, good. Okay. Sorry.
So you put him in the wrong camp.
Sorry, Roger Penrose. Sorry. Yeah.
So, well, I already said this. I think it had a good motivation. Like, it looked really promising initially, and I think it made sense to pursue it. And I would still say this today. It's just that it became increasingly more arcane, and they made it more complicated. And every time something went wrong, they came up with a weird fix for it, and it just made it more complicated. And they tried to sweep all these problems under the rug. And they just kept on working on it. And I think you're right that it's been a sociological issue in the community that has been fueled by the funding issues that we generally have in academia. And the reason it worked in the foundations of physics in particular is that you have this more or less total disconnect from experiment.
What about the CERN collider? They're trying to find new materials that spin off from a neutron or a proton when you smash it into another proton. Is this a waste of time? What are they doing here? There's something you talk about called the nightmare scenario. I don't know if I'm the Hadron Collider.
I'm not entirely sure what new materials you're talking about. So the Large Hadron Collider was primarily built to find the Higgs boson. And that's what it did. Now, they already have this huge machine anyway, so they might as well use it to look for some other things. And they've been looking for supersymmetry and didn't find it. So they've been doing this since the thing started, like more than 10 years. That haven't found anything. There've been a couple of anomalies, but they went away. There are always other things that you can look for and that you can make up, and then you can say, well, we looked for it and we didn't find it. By the way, your facial, you're giving yourself away. You'd be a bad poker player because you're going, and they were looking for things like this and they were finding this. It's so great to see. I can see you're kind of like, what you're saying really with your face is they haven't found a damn thing, have they, in 10 years? Yeah. Well, if you ask a particle physicist, they would disagree with that. They would say, "Oh, we've learned so many interesting things, and I don't know, we've seen some composite particles, and we have measured this and that thing to higher accuracy." And they're right, but I think, like, besides particle physicists, no one really cares.
There's no way to use what they found in other fields of physics. It doesn't bear relevance. What is it?
No. What? So, so when they build this thing and when they have to run it, there's a lot of technology involved. Big magnets. They have to be cooled with liquid helium, and so this technology has applications in other fields. For example, a lot of smaller particle accelerators are being used for medical purposes and stuff like this. So there's some connect between the technology that they're using and actually real world stuff. But when you're asking about, like, the discoveries that they've made, the answer is no. And this is why I think that we should have thought about this much deeper, like in the 1970s. Do we want to go down this road to higher and higher energies by building bigger and bigger colliders? Because I think if someone had actually thought about this in the 1970s, that they could have predicted that those particles wouldn't be good for anything in the next, 10,000 years. Wow. Just because you need all this big energy, and they could already have known that any new particle they would detect would be super short-lived, like we're talking like nanoseconds or something like that, picosecond, whatnot. or they would interact very, very weakly, like the dark matter stuff or neutrinos and things like this. And for both of these reasons, you can't actually do anything with them. So, I mean, again, like there's this aspect of curiosity. We want to actually know what the world is made of and what's going on out in the universe with dark matter and so on. And this is all well and fine. But I think, like, strategically, you have to ask, like, is this like the next thing that we should be doing? Like, do we actually need to go and look for the last quark and the Higgs boson and so on? Wasn't there something better we could have done with all that money and all this effort?
Well, the problem is you have people that have been doing this for 40 years. What you're really saying is, hey, you guys, you've wasted all your time. Your life has been a waste, and it's brought us nowhere. That's a hard thing. That's a hard pill to swallow. That's like killing a vampire. They take everybody with them. That's like, you know, it's hard to look yourself in the mirror and say, this thing I've dedicated my life to and built a reputation on, and that I've been teaching a whole generations of physicists is irrelevant, isn't even a thing. But there is slowly at least some admission from that camp, right? That maybe this has been a big waste of time.
Well, I have to say it's not publicly all that visible because people usually don't make big announcements.
Yeah.
But I've known quite a few people who, after seeing that the LHC didn't find supersymmetry and it didn't find any new particles, shifted their focus on something else. And a lot of those particle physicists, they're now doing more astrophysics. So it's kind of very closely related. So it's quite an easy change of direction to make. But so it's definitely had an impact. And I know that a lot of people are kind of, you know, depressed almost, that nothing happens. They don't really know what to do. But you have in academia, you have this huge inertia that things just keep going because they can't stop. Like, what are they supposed to do, right? Yeah. So as long as the money comes in, they'll keep going.
Why the money? How did they game the system? They were just very good at finding the money, getting people who probably don't understand these things on a very deep level. I guess there was a good PR program, yeah.
I think it's mostly for historical reasons. You said this at the very beginning. It was like with World War II, people saw that physicists can get very, very dangerous. And they thought, like, we need to have an eye on what those people are doing. And also, it can be really useful. And I think it was out of this thinking that atomic physics, nuclear physics was funded so much, because they were thinking, you know, this is something we need to do. And it looked very, you know, that there's a lot of good stuff that came out of it, like, nuclear reactors. And they were trying to get nuclear fusion to work, which we still haven't figured out. And, you know, we've understood the structure of matter and so on. So lots of good things came out of this. And then we went from the nuclear to the subnuclear regime and beyond that. And the money kept on coming because no one wanted to be the person to say, okay, I think we've put enough money into this. Let's just keep going.
Yeah, that really does sound like it's a major problem. Have you been what has happened to you as a result of the fact that you've kind of taken on the physics community this way? Because you've been pretty vocal about what a waste of time a lot of this has been. Has it been, you know, I have to mention this. You are a woman in a field that is almost all male. That had to have been already a rather lonely place to be, maybe, I don't know. Or at least it just feels like, just by the nature of numbers, sometimes it's harder to be taken seriously, harder to be heard. It's just the way it is. I mean, if you've got a bunch of dudes over here and then one woman over here saying, excuse me, guys, maybe all these toys you're playing with, can you guys get over? We got to do some work here. I mean, it must be a lonely, daunting task.
Right. So, first of all, I know I've said this twice before, but it's not that I criticize the entire physics community.
Right.
I've criticized some very specific things.
Yeah.
And I have to say, like a lot of physicists, I've gotten a lot of feedback from people in other fields than particle physics who are like, I totally agree with you. And it's an even bigger fraction if you look at people who've left academia. So there are a lot of people in academia who don't want to criticize others because it doesn't look good, and they're basically playing the same game. Mm. And so this drives a lot of those problems. People are just afraid to speak out. Now you're asking why was I the one to say it? It's very hard for me to tell how much it had to do with me being a woman. I've always been somewhat of an odd outsider, not just because I'm female, but also because I originally didn't study physics. I studied mathematics. So I've always come at it from a somewhat different angle, where I was just trying to figure out how much can you actually do with mathematics. I wasn't so invested into any particular approach like supersymmetry or, loop quantum gravity, string theory, whatnot. I looked at everything, I was trying to figure out how the maths work, what can you actually do with it. So I've always been more like, the onlooker, so to say. Yeah. And this kind of naturally moved me into this position of a critic of what was going on. So I think that's what happened. Yeah.
So, but now you're working. We should talk about what you're kind of like working on and what your theory is. You talk about superdeterminism. What about that? If it turns out that superdeterminism is wrong, what do you think is the next best theory? And is superdeterminism? Can you explain what that is? Because there's determinism, which I think I understand, but superdeterminism sounds wild.
Yeah, so first of all, it's not a theory. Superdeterminism, like determinism, is a property that a theory can have. Mm. And right. Everyone who works on this is like unhappy with the term superdeterminism, which was coined by Bell, like the Bell's theorem, Bell, in I think an attempt to dismiss it. Like he was trying to make fun of it, like, well, superdeterminism. So what it really is let me try to explain it this way. You probably know the double slit experiment. Like yes. Everyone has heard of this, right? So and the most exciting case is when you do it with single particles, like say photons. Okay, so the photon seems to actually go through both slits at the same time and then interferes with it. And when it comes on the screen, it's only in one dot, like it's only in one place because you're measuring position. But if you repeat this, you build up this interference pattern that comes from the wave. And the only way you can explain this is to say, well, it was a wave function that actually went through both things. So if you're trying to explain this like classically, where you're trying to say it's either a particle or a wave, it doesn't work. It really needs to be both. And then this weird thing happened that if you measure the particle, or you try to measure the particle in one of the slits, the interference pattern goes away, even if the particle doesn't go through the slit where you're looking. God. So it's like the particle knows that you're sitting there and you're looking at it. And,
yeah, this is where the
decides, now I need to go through one only.
This is where the debate with physicists about consciousness, like maybe it's immeasurable, right? I mean, this is where we get into that. Your ability to be conscious of this is actually affecting it's so crazy. That's the collapsing cat theory, right? I mean, you can extrapolate.
Yeah. Basically, so it's a question like what happens? Like, so how do we explain this? What's the role of the observer? And like in the early days of quantum mechanics, there was a lot of talk about does consciousness actually matter? So that there are still some physicists who think that consciousness plays some kind of role one way or another, and we can talk about this. But I think most physicists at this point think it's nothing to do with the human brain or consciousness in particular. It's the act of observation that could also be done by some kind of apparatus. So you put some measurement device there. But the weird thing is that if you are trying to explain what's going on by saying, actually, the particle was only in one state, it doesn't work, right? Because it can either, you can say, okay, it actually did go through both slits, then you can't explain the situation where you observe what's going on in one of the slits, or it's a particle and goes through only one, then you can't explain the other situation. And so that's the basic conundrum. So if you want you look confused.
No, I mean, it's because it's not, just not the way, yeah.
Yeah, that's exactly, like, everyone's confused about this, like, what the hell is going on?
Yeah.
And so in a nutshell, the idea of superdeterminism is just to admit that the particle knows what you're going to measure. And you can make this mathematically precise, what it means. So basically, you're introducing some sort of hidden variable. The hidden variable determines what the particle does. Does it go through one slit, left, right, or through both? And that hidden variable has to depend on what you measure. So that's like this is the formal definition for superdeterminism, is that these hidden variables depend on what you're measuring. And a lot of people say, well, that's more weirdness than I want to have. and I understand that. Honestly, I know why people think it's weird, but it has one big advantage, which is what Einstein worried about, is that in quantum mechanics, you have this spooky action at a distance that happens when you make a measurement, that suddenly this wave, the wave function, if you want to be technical, goes away, and suddenly it's only in one place. And this, in quantum mechanics, it happens instantaneously. It happens faster than the speed of light, and it just doesn't fit together with Einstein's theories. So this is why Einstein didn't like quantum mechanics.
Yeah.
And so you can solve this problem with superdeterminism. And I think Einstein was right, basically. We shouldn't have this spooky action at a distance. And the only way to get rid of it is superdeterminism.
So the only way to get rid of that spooky action at a distance is to not somehow observe it, but to use instruments to do the observing. I mean, is that, did I miss anything?
You can still observe it. So it doesn't really matter. I mean, it's a little bit more.
But when you observe it, you change it, right? So how do you, what is the variable you're throwing in there?
Yeah, well, what I'm trying to say is, like, you could do the observing on your apparatus, like you're watching where the needle goes, but actually at the end of the apparatus, there's a long cable and it goes into some kind of, I don't know, photon detector or whatnot, that you have somewhere else. And then
there's sort of a barrier.
Measurement.
Yeah.
Yeah, so there are several steps in between, and you're just at the end of the chain,
right? But
actually, the measurement happens already with the first device. Like, basically, when it gets
why in the world do you think this happens? It's such a spooky thing. Nobody's figured out why the observation of something can collapse the cat or not collapse the cat. What is that about?
Yeah, well, that's the key question, right?
Is it just different universes? Or, I mean, this is where the multiverse comes in and all that stuff, yeah?
Well, so one of the leading theories is that it's got something to do with the interactions with the environment. It's this idea of decoherence, and for a variety of reasons, I think that this doesn't really work. I'm more sympathetic to the idea from Roger Penrose, who already came up, who has this idea that it's got something to do with gravity. So there's actually something. You probably know that we don't know how to quantize gravity. So gravity is a non-quantum theory, and that's a big headache because we don't know how to combine it with the quantum theories in particle physics. So a lot of people think that we need a theory of quantum gravity. But another possibility is that gravity just isn't a quantum theory. And so you somehow have to prevent these quantum effects from leaking into the gravitational range. And that naturally brings up the possibility to say, well, whenever the quantum effect wants to get too large, because now you're trying to make a measurement, which is effectively an amplification, right? You're like a photon detector is literally an amplification device, and then it creates a current that goes into your computer, which goes into your eye, and then you can do something in response to that. So with every step, you're bringing this quantum state to a larger consequence, so to speak, right? So it becomes macroscopic, and somewhere along this chain, it needs to stop. And so Penrose is saying, well, it's got something to do with the strength of the gravitational interaction or with the gravitational self-energy or something like that. And so, we can debate whether that's exactly the right quantity to look at. And I think that this model has a couple of problems, but I think it's a plausible explanation. And there are other people who are looking at easier things, like you could say, well, maybe it's the mass of the objects. I don't believe this. I think it's a fundamentally flawed idea, or maybe it's the number of particles or some combinations of those. But I think this is the question that we need to answer. Like, what's the thing that actually makes the quantum effects go away? What is it? And so the interesting thing is that basically, now that they're building quantum computers, they're pushing into this range where they will have to answer this question at some point.
Yeah, I was going to ask you.
They're getting it. Yeah,
I was going to ask you what would convince you. What experiment would have to happen to bring you over to that side versus staying on this side, right? I mean, so, You mean that superdeterminism is wrong? Well, or just the idea that, I guess what I keep seeing is there's a lot of disagreement here, right? And there's 1,000 different disagreements, but we've got to get closer to, for lack of a better word, the truth of what's actually going on here. And I don't even know how you would, I guess you guys are all in the business of figuring out through modeling and experimentation how to replicate the same findings so you get closer to a deeper understanding of what's actually going on. That's the race here. That's the idea, isn't it? Otherwise, it's all theory.
Well, you mean replicate what we've already measured?
Yeah.
So, well, we know how to do this. Like, I've literally written a paper about how you can use superdeterminism to get exactly the same results as quantum mechanics, but that's kind of the uninteresting case. And the model has some problems, which I knew this. Like, it was just an example to say you can do it. But the thing that you want to look for are such deviations as Penrose, for example, predicts for his model. And there have been some experiments who looked for it. I think that Penrose's model is not super deterministic. I'm just mentioning this as an example. But you can, in principle, do the same thing for superdeterminism. And
so before you go on, let me ask you. You're saying Penrose model of what? What is it's a collapse model. Yes. So it's like the act of a measurement, all this quantumness has to disappear, and that's called the reduction of the wave function or the collapse of the wave function. It's like when you have the wave function that hits the screen, and suddenly you get a measurement only in one place. Yes. Like, so what happened with all the rest of the wave function? Yeah.
So that's the question you want to answer, and there are a couple of and so basically in standard quantum mechanics, it's just a miracle happens, right? So it's just poof, it's gone. And so there are a couple of collapse models which, they propose a physical process for this collapse, and they make more sense. I think that all existing collapse models still have problems because they're not super deterministic. Of course, I think the real collapse model would have to be super deterministic, but the idea is kind of the same in the sense that you write down the collapse model, you make predictions because it's got to have some deviations from standard quantum mechanics, and then you have to look for them. And the issue with all those collapse models is that the physical collapse is competing with decoherence, which is basically noise. So it tends to cover up everything. So you have to find some kind of experiment where you don't have this decoherence problem. And this is why quantum computers are so interesting, because they're making a lot of effort to get rid of this decoherence so they can do their computation. And they're building bigger and bigger devices, which is exactly what you want to do to test this kind of collapse model, which brings up the question, like, will there be a limit where they just can't create larger quantum states anymore because the state will inevitably collapse because they've reached this threshold?
That's as you're speaking, I keep trying to figure out, or I keep going back to Schrodinger's cat, because you're talking about the collapse model. You don't, but there. Let's just get into consciousness for a second, because it's not a word you like, I don't think. And yeah, it's a little wishy-washy for you, right? But is it fair? Let me see if I can do a layman's sort of what physicists talk about when it comes to consciousness. There seems to be something about the observation of, so when I observe as a conscious being, with my naked eye or whatever, without the buffer of instrumentation, the cat will, in the box, when I open it, will either collapse or it will be alive. And maybe before it's been observed, it's both alive and dead. So it's a zombie cat. That's sort of the idea. And now you get into the phenomenon of consciousness itself, which maybe cannot be measured using anything we have on this planet, at least for now. It seems to stand alone. And this is where there's a big debate among physicists, at least there used to be, I don't know, but is consciousness a thing? Does it play a factor in trying to measure ultimate reality, superdeterminism, whatever it might be? Am I in the area here, or am I off?
Well, there are some physicists who have discussed this, and there are still some physicists who are discussing it. But I think that maybe this is just a sample bias from people I know. But at least among the people I know, they're very practically oriented, and they think that this collapse of the wave function of the cat doesn't require consciousness. It requires some sort of measurement apparatus. And even if it comes to your brain, let's forget about conscious awareness of the signal. I think you don't need this. What you really need is some kind of receptor that would be at the back of your eye or something. And then the signal is passed on as some kind of electrical signal. I'm not a neurologist, but basically that's the idea, right? It goes into some part of your brain and that lights up. And suddenly it's a big thing. So it's a big state because you've seen a big cat, or you haven't seen it or whatnot. Yeah. Right. And so this is what I meant earlier. So any kind of measurement is a sort of amplification process. Yeah. And in that case, it's happening in your brain. Now, you could say that if you become consciously aware of it, then it's an even bigger amplification because you could act on it, right? You could say, well, if the cat is dead, then I don't know, I throw it in a bin or whatnot. Yeah. So that's an even bigger amplification. But I kind of doubt that you have to go that far because, the parts of your brain are already macroscopically big.
Right. So where does are you a strict materialist? Meaning, do you think everything has?
I think so. Yeah,
you are. Everything has a measurable quality. You can measure. You can ultimately will be able to measure everything from logic to love to consciousness. If that's what you want to call it.
I'm not sure about the measurement because, as you probably know, in quantum mechanics, the wave function is actually not entirely measurable. It has this complex valued phase that is in principle unmeasurable, and so it's a little bit complicated. But when you're talking about things like what's going on in the brain, what did you say? Love, friendship,
whatever it might be.
So on.
Yeah.
Even
Even imagination, even the ability to come up with
Yeah, I
something
think
that
it's
isn't
all
there.
brain signals. So it's all physical. Maybe, I'm a physicalist if you want to put it that way.
But then
Yeah,
then
so I think
yeah.
it all has a physical basis. Yeah.
My follow-up question then would be, why is it there? What's it leading us to? Right? I mean, look, you spend all your time thinking about these very big questions, and you, at the end of it, are looking to find out what is really going on. I would argue that that's something like the truth. What's going on here? What is the ultimate reality? What is the theory of everything? Isn't that what you're really ultimately looking at? You have a brain that seems to be able to conceive that is a possibility. You can't stop reaching for it. I don't think that's a mistake. I think there's a reason for it. I think that there's I like to think of the universe as rather benevolent in terms of that there's a good answer to that, there's a bad answer. There are good ideas, there are bad ideas. There are good actions, there are bad actions. You might unleash something, you might find something very powerful truth. And when you do, you might be able to manipulate that truth. Like, for example, the splitting of an atom. Then it becomes, well, is Sabine going to actually use it for good or evil? I mean, you might become, power hungry, or you might say, I'm going to try to change the world. But this is here. This is in you. That's where I go. I always say that we can talk around about all this stuff, but at the end of the day, you, like myself, like this conversation, are looking to hit a mark. We're looking to hit a mark. And that mark is something like, at least it's in the direction of truth, in the direction of what's going on behind the curtain. So that's where I go. That's the imagination.
Yeah, it's actually, I think it's like one of the, theories of consciousness that is most preferred by physicists, is that it comes about because we're trying to understand and predict and ultimately also use the nature around us. So we're constantly trying to develop a theory or a model of what's going on, also a theory of each other. So by this time, you probably have a theory of me and I have one of you. And so we have a theory of everything around us. And so scientific exploration is basically a continuation of that, but on a societal level. And so it's a very good question, like, where will this go? Like, what are we going to do with it? Basically, what we're constantly doing is we're trying to figure out the universe.
Yeah.
Okay, so that much we know, but is there an ultimate goal to it or something? I don't know. It could be.
Well, when did you realize you were a physicist? When did you realize that you had these questions? What was the first question you had? Can you remember when this happened to you? And what is, I think, let me give you an example. So most authors, I'm a comic, so I'm probably concerned constantly with a question. I'm always, you could say the theme of a book is the author's argument for how one should behave in the world. And, I think all of us, it's very hard to get out of this question that we continue to try to answer. And we do that with story. I do it with my comedy. But I'm always asking really I've always been obsessed with what courage is. What is courage? How do you define masculinity? Why was I thrown into this? What is this instinct behind being a provider, protector, blah, blah, blah. I'm a slave to certain things. And it's an interesting question. What is the primary question in your brain? What are you constantly trying to think of? What are you trying to answer? You, Sabine, Hossenfelder. You're very German.
So, yeah.
Is that, I mean, yeah.
Close enough. It's a terrible name.
No, it's it's a very physics name. It sounds like it's got gravitas. You should have a very sort of Germanic name, yeah. So,
as I said, I originally studied mathematics. And the reason I went into physics was that I was fascinated by how much of the world you can describe and also predict with mathematics, which is like, you scribble little symbols on a sheet of paper and out comes an equation and you compare it with the data and it fits together. Like, to me, this is like, it's almost magic.
Yeah.
Like, we can calculate this and it describes what people observe. Like,
Yeah.
And so I was trying to figure out what mathematics does that. How does it work? Can we figure out? There's lots of mathematics that does not seem to describe anything we observe. Why is that? So how can we figure out what's the right mathematics to use? And also, are there some limits to what mathematics can do? So I've been very obsessed with this role of mathematics, maybe like you've been obsessed by the role of the courage.
Yeah. Yeah, that's, I mean, I envy you because it just sounds like math is such a hidden, beautiful world. Most of us are afraid. I mean, I took calculus and I was like, it was like I'd rather be in a dentist chair with no Novocaine. But that's because I never had anybody explain it to me. And then I heard, Eric Weinstein and I talk, a lot about that. I always ask him like about math and just, so there was a mathematician who was he saw a hawk flying and he was trying to sort of figure out how much of the globe that hawk covers in a half hour. And these interesting questions that you kind of like never think about, but math can be quite beautiful. Can you give me an example of where the math fits like a glove with physical phenomenon of how to explain something? Do you remember the first time that you saw that?
Well, I remember the first time that I saw it, but it's a rather abstract example. So it was quantum field theory, and we had homework that was calculating how an electron scatters on another electron. And it's a standard exercise. And I actually, I went into the library and dug out some experimental data and just for the fun of it, plotted the result of my calculation over the data, and it went right through. And I was so impressed. I was like, I did this. Like, I did the calculation, and look, it works.
Wow. Yeah.
It's a little bit silly. Actually, I realized later that this was a very lucky day, because normally it takes me like, 20 attempts to get all the constants right and the units and so on. But that day it worked. And so quantum field theory standard model is like maybe the obvious example. It's an extremely precise theory. It's frustratingly precise,
yeah.
Which is why they can't find anything better, right? And so I still find this super amazing. Like, we have this handful of particles with 3 or 4 interactions, depending on how you want to count. And they make up everything. Like, the entire universe is built up from only those particles, like all this complexity around us. You, I, the plants on my window, and so on and so forth. It all comes out of only those few particles and those interactions.
That's incredible.
And yeah, it's amazing. And of course, there are lots of things that we don't understand, notably how exactly does this complexity come about? Does it follow some kind of master plan? What do we even mean by complexity? And then we return to this question of consciousness, or maybe even, like a superhuman consciousness that extends to entire civilizations and so on. And so we have no idea where it'll go, basically.
It's amazing, though, that we figured out what the building blocks to the universe are. Because if you figured out what the building blocks to the universe are, and you can measure those mathematically, then maybe if you extrapolate, you'll be able to take those building blocks and build an entirely new universe, or build whatever's in your imagination. We're already kind of doing this with AI and probably gene editing eventually and all that. But, it's what I love about talking to someone like yourself, and I'm sure what drives you and all of us, is that most of the world is a mystery, right? It's a mystery. When you watch boxers and you if you don't know anything about fighting, and you watch the way they can slip shots and they get out of the way of a punch that's so fast, how the hell do they do that? How do you do that? And then, of course, when you go to a gym and after 2 years, you start to learn, well, it's where you stand, it's how you move, it's where you place your shoulders, blah, blah, blah. And somebody says, it's not about punching, it's where you punch from. And you're given a flashlight in a dark room, and you start to realize that maybe this isn't such a mystery. You watch a concert pianist, the way their fingers just bounce off. Then you realize there's a system to it. Now, you're going to have to get technically proficient, you're going to have to practice, but you can pull the curtain back a little bit in anything. And that to me is what drives me in general. I I love breaking down the mystery. I hate when there's a mystery and I don't know about it. And I'm sure you're driven by the same thing. And then math seems to be to get at the ultimate reality, the ultimate building block. It's not that it's going to give you, I always use the expression or the example. If you look at the Sistine Chapel, there is something that is irrational about it's what it does to you, right? So I don't need to know about anything other than that it's awe-inspiring. And for a second there, I'm just awed by what human beings can do under favorable circumstances. And then you kind of get into this idea there's got to be a God or there's got to be something benevolent because nothing could be that beautiful. And you just get taken away. There's a romantic truth to that. And then, of course, there'd be a chemist who would look at it and say, yeah, I know, guys, I hate to piss on your parade, but that's not yellow. That's just your eye playing a trick. And then Sabine would come in and say, yes, and, in fact, maybe it doesn't even exist because we don't know exactly what these quarks and we all go, hey, man, look, I get it. I get that there are a lot of different layers of truth, but for right now, I just want to stare at this tapestry because it does something nice to me. And that's also the problem. That's also the sort of thing that there's so many things to think about, and it's difficult sometimes to know whether you're headed down the right path. I'm sure the string theorists in their quietest moments are probably in their own minds saying, I've spent a lot of time looking over here, or maybe I've been at the bottom of a well and only looking at that sliver of the sky. And for 40 years, I've missed the entire sky. So keep it down, Sabine. Keep it down. You're inconvenient here, That's how I look at it. I don't know if that's a fair commentary, but.
No, I totally understand that. I know that a lot of people who work on string theory and similar ideas, they're almost philosophically driven, maybe even religiously.
Yeah.
Like they want to understand the universe. That's what they want to dedicate their lives to. And I understand that on some level. And I feel really bad for raining on their parade, basically. If I say, well, actually, I think you're not getting anywhere. But I also feel like someone's got to do it, basically.
Well, you do, because, you have come along and said, hey, guys, I don't see any results here. I mean, I don't see anything that's useful or that's even informing other fields of physics necessarily, or whatever it is that you're saying. I think that's fair.
Yeah,
I think you have to speak.
I'm actually, people tend to overstate my criticism of string theory. I actually think that string theory isn't necessarily the worst example because it does have some links to other fields of physics, not this big idea of the theory of everything, fundamental, whatnot, but the techniques, the mathematical techniques that have come out of it through describing things as little wiggly strings. You can use this for other stuff. So I wouldn't go so far to say that it's been completely useless, but it's pretty clear that it has totally grown out of proportion and it's sucked up a lot of smart people and also money.
What about Eric Weinstein's geometric unity hypothesis? You don't think it's understandable, but have you actually sat with him and had him explain it, or are you just going on what you've seen based on what?
Well, so he wrote a paper like a couple of years ago, during the COVID thing. I remember him putting out a paper. I read the paper and I listened to some of his lectures, and he's tried to explain the thing for me a couple of times. I don't want to say it's not understandable, however you phrase it. So, but I can tell you, I don't understand it. And I do understand the words that he's using. Like those are mathematical structures that I'm used to, like gauge groups, fiber bundles, pullbacks, and Lie algebras and so on. I know all these things. I still don't understand what he's going on about. And I've talked to other physicists about it, and they don't understand what he's going on about. So basically that gives us two options, right? So one option is we're all idiots and Eric Weinstein is a genius. We don't understand it. Or it's not a particularly useful theory. So I don't know which one's the right one.
Right.
So you could fairly criticize that maybe I haven't spent enough time on it. And that's probably true. I didn't spend a lot of time on it, though I did spend some time on it. But in my defense, I have to say, like, I don't really know why, because I don't see what it's good for. So I've never been interested in theories of everything. And I've written a whole book explaining why I think brand unified stuff is useless. So I'm not super motivated.
Right.
I love Eric, and I think he's a really bright guy, and I like arguing with him. I have a lot of disagreements with him, but he always has something interesting to say. Like, he thinks very deeply about what he's doing, and I appreciate that. But it still doesn't convince me of geometric unity.
Well, you've written 2 books, Lost in Math, and your newest book, Existential Physics. Can you, was Lost in Math the first sort of critique of what's going on in physics? And what is the difference? What's the continuation? When you have Lost in Math, what is existential physics? What are you arguing in that book as well?
Yeah, so Lost in Math was basically a community criticism. It was also my attempt to try and understand people. So I traveled around and I interviewed a lot of people, and I was trying to figure out, like, why are you doing this? Like, so if it's not going anywhere, like, what's your motivation?
What answers did you get?
Well, some people, like, they openly said, I want to work with a beautiful theory. And if it's not beautiful, I'm not interested. So, which to me raises the question, like, so what if the true theory is not beautiful?
Well, it sounds like you're coming at it with such a heavy bias. You're trying to, no matter what, you're going to fit a round peg into a square hole. No matter what, you're going to shoehorn it if you need a shoehorn and some butter, right? I mean, that's a tough way to do science, isn't it? Because this is going to be beautiful no matter what. I'm a romantic. That's how I am, by the way. I just look at everything romantically.
That's right. But you have to understand, like, there's a whole generation of physicists now who they went into the foundations of physics with that thinking, like, inspired by books by Michio Kaku and Brian Greene and so on. And Eric Weinstein, not Eric, Steven Weinberg, Dreams of a Final Theory, and all those kinds of stories. They've grown up with this belief that we're working on this beautiful final theory that's coming into being, and this is what they want to do. And I would say, well, if that's your motivation, that's not really scientific, right? As a scientist,
it's romantic.
Exactly what you say.
It's romantic.
You need to be open-minded about whatever nature does. Like, you look at what you find and then you try to explain it. You don't come with this preconception that it has to be this elegant, beautiful, and whatnot. In any case, so this is what I wrote the book about. Now, I was also trying to explain that all these predictions for the Large Hadron Collider for supersymmetric particles, dark matter, and so on, were very, very unlikely to become true, because they were all based on arguments from beauty. And would you know it, I turned out to be correct. So
yeah, what a disappointment, though. I mean, do you find yourself wanting it to be beautiful as well? Do you find yourself being caught up in the romance, in the notion that the universe is ultimately, when you say beautiful, what you're really saying is it's benevolent? That there's a benevolent direction that everything is going, right? We're all being nudged in the same cozy direction, and at the end of the day, it'll all be okay.
You know, it's interesting if you look at the history of physics, and there are historians who have done that, so it's not my idea, but our conception of what counts as beautiful in the laws of nature has changed over the course of time. And it's adapted to what's actually worked, like what we found nature to be like. Like, for example, when quantum mechanics was discovered, a lot of people thought it was ugly. That's literally what they said. And now, a century later, I think nobody would call it ugly. You know, they have problems with it. Like, we don't understand it and so on, but the maths is fine. You know, it's basically linear algebra, as they like to joke. Yeah. So I think that's an odd way to look at it. This is what people would say today, and there are similar things with elliptic orbits of planets. You know, people thought it was ugly; it had to be a circle. because circles are, if God had any choice,
they're tidy. Yeah,
exactly. Right. And so today people would just say, well, that's ridiculous. So it's an ellipsis because that's how the laws of nature are, right?
Yeah.
And so over the course of time, our idea of what's a beautiful law of nature has changed. And so I'm not worried that whatever fundamental theory we'll find will not be beautiful. I just think we might not have the right idea of what's beautiful yet. But we'll come to find it. And I've said this on other occasions, but I think that there's basically chaos and complexity plays a much bigger role in the foundations of physics than physicists want to admit at the moment. And personally, I think, if you've ever looked at a fractal or something, they're much more beautiful than this strict, regular symmetry that you find in particle physics at the moment.
Is it possible, when you mention fractals, that everything is a fractal of itself? I mean, is the fractal theory something that you could play with? Like if you learn
a fractal of itself.
If you knew how the human cell worked in its entirety, you would know how the universe worked.
Oh, right. That's an interesting question. I actually addressed this in my second book.
So, good. So that's great. So
maybe I'll come back to. So you asked, like, what's the first book? What's the second book?
Yeah.
So and the first book was like this criticism, and I actually got quite depressed about it because it's not.
I don't blame you.
I don't like to think of myself as this person who always said, no, you can't do this.
You're the party pooper. You're the party pooper. You're the physics party pooper. Yeah. Yeah.
So I wanted to write another book which explains what's so fascinating about the foundations of physics. And so I went through all big questions, like, for example, could there be universes inside of particles? So it's one of the questions in the book. And also there's the question of free will that I'm addressing, and entropy. Will the universe eventually run out of fuel? Stuff like this. So every chapter in the book is a question I try my best to answer. I also write about the multiverse, and some.
I'm going to definitely read this book. I'm definitely going to read this book. I always
it's much more optimistic than the first one. Yeah. Yeah,
I always try to read the books, but frankly, I was too intimidated. I thought to myself, I'm just going to talk to her first and see, because I don't know if it's going to be, when you say lost in math, I'm like, math is going to be tough for me, but explaining existential physics that way I'm very interested in those questions. So I'd be very interested to hear your perspective on all of those. You're basically in existential physics, you're tackling all the big topics in physics that are out there in the zeitgeist.
In the foundations of physics. Yeah, well, the origin of the universe, free will, all that kind of stuff. Yeah, it's all in the book.
Great. Well, Sabine Hossenfelder, I appreciate you joining us, man. It's really interesting. I hope you come back, because what I'm going to do is I'm going to now read the books. And then I'm going to have a lot more questions, because I'm going to get over my fear of physics, which I think a lot of people have, and it always does feel like you guys are all working in some dusty lab with bad lighting and asking questions that in your own mind and opening dusty books. I mean, there's a lot of dust in my imagination and poor lighting in the world of physics. But I know that's my layman's ignorance. So,
to some extent, I wish that was the case. The reality is a little more, a little busier, let me put it that way.
I'm sure.
But if you want to read the book, I'd recommend start with the second one, because in hindsight, I understand that the first one is kind of hard to read in places.
Yeah. Final question: are you working on your own theory? I know superdeterminism is something you touched on, but is that what you're are you putting forth your rebuttal to string theory and the things that are going on?
Well, so I don't see superdeterminism as a competitor to string theory, because it's not really a theory of everything. It's really trying to solve this one problem with the measurement process. And naturally, I think that this will solve other problems. But, I think let's take it one step at a time. So awesome. That's my attitude. And yes, I'm working on this. I'm actually trying to work on exactly the question that you asked earlier, like exactly what would you look for? Like, what's the experiment you actually want to do? And I'm happy to report that I had a great insight like 2 months ago.
You did?
That I'm trying to work out. It's basically it's a variant of Penrose's idea with the gravitationally induced collapse, but in a way that I think it'll be compatible with superdeterminism and with Einstein's theories. And so I'm hoping to pull this together and make some predictions for actual experiments. Yeah.
I hope you're right, and I hope you win a Nobel Prize. That'd be pretty cool.
Yeah.
And then somebody will come along 100 years later and say, Sabine Hossenfelder was wrong about this one particular thing, and now I'm going to get a Nobel Prize. And so it goes, right? And so it goes. So I appreciate your time. Thank you for educating me. And I'm sure the audience will appreciate it as well. So I hope this is only round one. I hope you come back for round two after I've educated myself further.
Sure thing. Lovely to talk to you.
Great to talk to you. I'll talk to you later. Thanks so much.